Hey there, you rates. Mr. Herman here, and this lesson is exercise 3F, terminating, recurring, and rounding decimals. Learning goals for this one is to understand the meaning of the words terminating and recurring decimal, and to understand the different notations for recurring decimals through dots and dashes. The success criteria for this one is to be able to convert a fraction to a recurring or terminating decimal through division, and to be able to round decimals to a given number of decimal places by finding what's called the critical digit. Now, terminating, recurring, and rounding decimals, we have to note that there's quite a bit going on with this one. Just like the previous two exercises through remote learning this week, a few rules that we have to take into consideration, but quite a few of these you hopefully would have seen within Year 7, fingers crossed. So, not all fractions convert to the same type of decimal. So here we've got three different examples here of converting a fraction to a decimal. This half is also depicted as 1 divided by 2, because that's technically what it is. We're getting a numerator and dividing it by our denominator. So divisor, dividend, 1 divided by 2, this is equal to 0.5. So this is saying that half and 0.5 are the same thing. They're just written in a different format. One's in fraction and one is in decimal. And you notice that 0.5, it just kind of stops. It doesn't keep going. There's no numbers or digits afterwards. Technically, you can put zeros afterwards, but that becomes rather redundant. So we just leave it at 0.5. But the second fraction here, 1 over 3, this is the same as getting 1 and dividing this or splitting this up into 3 parts. As a decimal, if you were to put this into your calculator, you'll notice that it has a 0.33333 and it keeps going. Obviously, it stops within a calculator. I've just got my trusty calculator here. If I were to put 1 divided by 3 on the calculator and convert it from fraction to decimal, you'll notice that it keeps going 33333. And the reason why it stops is because there's not enough room within the screen for the calculator to display more information. And the second thing is because there's not enough memory for the calculator to actually store that many 3s to indicate that it keeps going. So 0.33333 generally we indicated by dots to indicate that just keeps going on forever. And the last one is 1 over 7, which is 1 split up into 7 parts, 1 divided by 7. This as a decimal, and you'll notice that it's 0.142857 ... So again, if I were to put this into the calculator, 1 divided by 7, and convert this into a decimal, 1428571, 1429. Now, you will notice that there is a pattern, 142, 142. This is a 9, this is an 8, and there's a reason why this changes into a 9. Obviously, there's not enough room, but it does a rounding thing based on the critical digit. We'll get to this in a second later down the track. But these are the 3 different types of decimals that you can get. So let's have a look. Let's investigate this a bit further. What we have here is a terminating decimal. And a terminating decimal has a finite number of decimal places, and finite it just means the opposite of infinity. It eventually has to stop. Okay, a finite just means eventually it has to stop. Eventually stops. Okay, so finite eventually stops. It has a finite number of decimal places, so it terminates. It terminates just means to stop. Okay, so for example, 5 over 8. If we did 5 divided by 8, this is 0.625. And how you actually work this out is you see how many 8s go into 5. Now this technique here, I will do an example to see what's going on. But you can see there's a 5.000 just to make this 5 go into 8. And eventually, when these carryovers keep going on, you'll end up at a point where there's no remainder. And when there's no remainder, that's when we know that it stops. If there are always remainders, in some cases there will be, it will just keep going and going and going. For 5 over 8, this terminates, and so the decimal equivalent is 0.625. A recurring decimal, or also known as a repeating decimal, has an infinite number of decimal places. So infinite, we all know infinity, it just keeps going, as an infinite number of decimal places with a finite sequence of digits that are repeated indefinitely. So this sentence just means that you might get a set amount of numbers that keep going. For 1 over 3, A finite sequence is just simply 3. So when we figure out how many 3's go into 1.000, there's always this constant remainder of 1. So we're getting 3 into 10, 3 into 10, 3 into 10, and this keeps going and going and going and going and going. So our recurring decimal is 0.3. This is the finite sequence, number 3. And you might get different types of finite sequences. You might get some answer that goes 0.272727. In this case, a finite sequence is 27 because this continuously keeps going after the decimal point. And obviously, we've as mathematicians, we try to find shortcut ways of doing set notation. So a convention is to use other dots that are placed over the digits to show the start and finish of a repeating cycle. So for example, 0.555 that continues on just can be written as 0.5 with a dot on the top. So this is just to indicate that that 5 just keeps going on forever. Or another example is 0.3412412. The repeating numbers is 412, and then it goes again 412, 412, etc., etc. So another way of indicating this is writing 0.3 and putting a dot above the numbers that start or end within that finite sequence. And so we know that 412 keeps going, so we put a dot above the 4 and a dot above the 2. So that is the same as this. It's just written in the short hand notation. But then another convention that we can use is also a horizontal line that is placed above the digits, and this again shows a repeating cycle of digits. So again, you can do 0.555 as a line above the 5, or 0.3412412. You can just have a line above 4, 1, and 2. And that's just to indicate that 4, 1, 2 keeps repeating forever. The general rule of thumb that I know is that if it's a single digit that keeps repeating, you generally use a dot. But if it's more than one digit, say it's 2 or 3 in this case, you would use the line. So the dot, or the dot for this and the dash for this. Another skill that we're going to be looking into is rounding decimals. And I know you guys have seen rounding decimals within year 7. This is a skill that you really got to hone into come year 9, year 10. And not even just in school, but in the outside world, knowing how to round decimal numbers. It can be as basic as money, or as complicated as knowing how many a certain number goes into another number when in carpentry or trade of some sort. If you're not good with your rounding, you can come into situations where there's quite a bit of error, and that doesn't really look good in your behalf. So rounding, you've got to be really good with rounding. So rounding decimals involves approximating a decimal number to fewer decimal places. So obviously we don't want to have a number that just keeps going and going and going in a decimal. So we want to truncate it, we want to cut it at a certain point. So when rounding, there's this thing called a critical digit, and this critical digit is the digit immediately after the rounded digit. So for instance, if we want to round a number to 2 decimal places, the critical digit is after the second decimal place, which is the third number. If we had a number that is 0.386529999, etc., 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 and we want to round to 3 decimal places, the critical digit will be the number after the third decimal place. So this is the first, second, third. Our critical digit is the one immediately after the third, which is the fourth. If it was the fourth one, the critical digit would be the fifth one. If we're rounding to the 1, 2, 3, 4, 5, the sixth number, our critical digit would be this one here, etc. Okay, so we'll be looking into critical digits. And we also got to note that if a critical digit is less than 5, then the rounding digit is not changed. And if the critical digit is 5 or more, the rounding digit is increased by 1. So again, this is the set of rules that we have seen before. What you probably haven't heard of is knowing that the digit after is being named the critical digit. Okay, so in this example here, 51.34721 rounded to 2 decimal places, it's 51.35. The reason why is because if it's to 2 decimal places, 1, 2, the next one is a critical digit, and we're just following the second rule. If the critical digit is 5 or more, so this critical digit here, 7, which is more than 5, the rounding digit, so the digit beforehand, is increased by 1. So that 4 bumps up to 5. So this becomes 51.35. And we'll do an example just so we can get better familiarity with this. All right, let's have a look at some examples here and how to tackle these examples. Example 17, we're going to write terminating decimals, and we're going to convert the following fractions to decimals. Now, some of these we could know off by heart. I know that 1/4 is also the same as 25% or 0.25. But if we want to look at the actual process of converting it from a fraction to a decimal without a calculator, and you didn't know this actual number was 0.25, you would find out how many 4s would go into 1, or how many denominators go into the numerator. Now this is kind of weird because we look at this, we go 4 into 1. That doesn't really make sense because 4 is actually quite a bigger number and 1 is smaller than 4. So we manipulate this by putting a decimal point and then just putting a 0 there, because 1 and 1.0 is technically the same thing. And now we've got something to work around this. So 4 into 1 obviously we can't do, so we'll take that 1 and carry it over. And here a decimal point from the previous skill lines up. 4 into 10, so that goes twice. So 4, 8, and then we have 2 remaining. We have no 2 to add to this, so we just again put another 0. So now we are doing 4 into 20. 4 into 20 goes 5 times. Exactly 5 times, so we're no remaining, so we stop here. And so this is where we get a 0.25. So 1/4 and 0.25, exactly the same thing. One is just written in fraction format and the other one in decimal. Second one is how many, what is 7 over 8 as a decimal? So again, we find out how many denominators go into the numerator. Obviously we know this is going to start with a 0 point, and we obviously can't find out how many 8s go into 7, so we cross that and put it into 70. So how many 8s go into 70? We know that it goes from 8 to 64. 8 times 8 is 64, and we've got 6 remaining. So 8 into 70 goes 8 times. Now if you're a bit unfamiliar with your division, you can always use your multiplication table, the 12 by 12 table, to help you out. Alternatively, you can use your calculator. I don't want you to rely on it. I want you to really practice this skill. But if you're feeling a little bit unsure, you can always use your calculator just to check how many 8s go into 70. In this case, 8 into 70, we've got 8 times, and we've got 6 remaining. So now we need a 6 to compensate for here. 8 into 60, 8, 16, 24, 32, 40, 48, 56. This goes 7 times. 56, and then we've got 4 remaining. So 56 to 60, we've got that 4. Again, we need another 0. 8 into 40 goes exactly 5 times with no remainder, and that's when we stop. So right here, these are terminating decimals because there are no remainers that continue, and our solution in this case is 0.875. So 7 over 8 is the same as 0.875. A second example here, example 18, writing the recurring decimals. And now we're going to look into decimals that do have a consistent remainers that appear afterwards. So 2 over 3. We're going to see how many times the denominator goes into the numerator. I might write this actually a bit lower. There we go, that's better, so I can have some space at the top. So 3 into 2, obviously we can't do. But 3 into 20, that goes 3, 6, 9, 12, 15, 18, that's 6. The 2 remaining. Hey, hold on a second. 3 into 20, that's 6. With 2 remaining. Okay, I see what's going on. 6, yada, yada, yada. This is going to keep coming up with a 2 remaining, and if we keep putting a 0 there, this is just going to keep going and going and going. So 2 over 3 is equivalent to 0.6. And because this keeps going, let's just use that shorthand notation with a dot on the top, and that dot just indicates that that 6 keeps going on forever. And the second example for this one, we're going to look at 3 and 5 over 7. as a decimal. Now we know that this is going to be 3 point something 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 because of this whole number. The whole number is 3. It's going to start off with a 3. Okay. What I care about is more how many 7s go into 5, how many times the denominator goes into the numerator, and then we can just showcase this answer afterwards after we find this out. So how many 3s go into, how many 3s, let's try that again, how many 7s go into 5? I'm just going to raise that a little bit so I got a bit of space. And you know there's a point here, so 7 into 5, can't do. 7 into 50, 7, 14, 21, 28, 35, 42, 49, that is 7 with 1 remainder. 7 into 10 is 1 with 3 remainder. 7 into 30, 7, 14, 21, 28, that is 4 with 2 remainder. Now this goes for me so effortlessly because I'm pretty aware of my times table, my 7x7 times table. But back when I was in year 8, this would have taken me a while. Okay, it just takes practice. It just takes practice and familiarity with your times table. 7 into 20, that's 7, 14, which is 2 and 6 remainder. 7 into 60, 7, 14, 21, 28, 35, 42, 49, 56, so that is 8 with 4 remaining. 7 into 40, and this just keeps going and going and going. 7 into 40, 7, 14, 21, 28, 35 with 5 remaining. And then 7 into 50, again, this is now just going to repeat because we've already done our 50 over here. And if we keep going, we know we're going to go 7 into 50, which is going to give us that 7 and then the 1 remainder, etc, etc, etc. So as soon as you see that what you're carrying over has already been completed before, that's how you know you're meant to stop. So our answer in this case is 3, and 5 over 7 is the same as 3.71428, and this process continues on forever. So I'm going to put a line across from 7 to 5 to indicate that this sequence of numbers will keep going on. All right, let's go into rounding. Now, I just realized I made a mistake. I recorded and made a bit of a boo-boo, so I've just had to backtrack. Round each of the following to a specified number of decimal places. So to 3 decimal places, this is going to be 15.357, and the critical number after the 3rd decimal place is this 2. So right here, this is a critical number or critical digit. So this number here will determine whether that 7 stays the same or gets bumped up by 1. In this case, it stays the same, and the reason why is because if we look at the previous rule over here, if the critical digit is less than 5, the rounding digit is not changed. That rounding digit, which is a 7, stays unchanged. So to 3 decimal places, our number is 15.357. It's been truncated, it's just been chopped, and just to determine if that 7 gets bumped up by 1, we look at the critical digit less than 5, so it stays the same. With B, we're going to round this to 4 decimal places. So our 5th number is going to, or 5th decimal place rather, is going to be the critical digit 1, 2, 3, 4, 5 over here. So this is our critical. And again, we're just going to read the rules. If the critical digit is less than 5, the rounding digit has not changed. In this case, the critical digit is 5 or more, so the rounding digit is increased by 1. It's increased by 1. So this will be 4.86. Now, this here, 5 makes the 9 round up to 1. But we're now in a scenario where if this rounds up to 1, it turns into a 0. And as a consequence, this is now also rounded up by 1. The 1 over here gets rounded up by 1. So in this case, this will be 4.8620. Okay, in other words, 19, because this is 19, that 5 there bumps it up, and that digit after 19 is 20. Okay, that's how I like to think of it. Now, obviously, it wants to 4 decimal places, but because of that 0 there, it kind of comes redundant, so you can just write it as 862. In some scenarios, you would keep that 0 there, depending on what information is important or relevant to the question. In this case, you would just leave it as 4.862. Okay, so be very careful with these 9s here and what ripple effects they have with the digits beforehand. The last example here is rounding a recurring decimal. So we're going to write 3/7 as a decimal corrected 2 decimal places. So let's first find out how many denominators go into the numerator. In other words, how many times does 7 go into 3.00000, etc. Now, we just put this decimal point here and continue with 0, because obviously we can't get 7 into 3. Cross it out. 0 into 30, 7, 14, 21, 28. There's 4. The 2 remaining. How many 7s go into 20? 7, 14, which is 2. With 6 remaining. Now, let's have a look at this. This is a scenario where I've seen many students, they say, oh, as the 2 decimal places, oh, it must be 0.42. I don't have to keep going. Well, we actually have to keep going because we need to correct it to 2 decimal places. We don't know if this is going to stay as 0.42 or it might get bumped up to 0.43, because we need to know what the critical digit is. We need to know what that 3rd digit is, whether it's less than 5 or 5 or more. Okay, so let's see how many times 7 goes into 60. 7, 14, 21, 28, 35, 42, 49, 56, which is 8. The 4 remaining. Now, obviously, we don't have to keep going. This critical digit is more than 5. Okay, this critical digit is more than 5. So 3/7, when rounded to 2 decimal places, will be 0.43. So not 42, 43, because this 2 now gets bumped up by 1. Now, I haven't put an equal sign here. I'm putting an approximation sign. So this little squiggly here, this just means approximately equals to. Approximately equals to. And the reason why I put this here is 3/7 isn't exactly 0.43. In fact, it's 0.428, yada yada, keeps going. Right? So if I were to put in the decimal place number of this, I would purposely put the equal sign there. And that way 3/7 will be exactly equal to whatever this forever long decimal number is. But because we've truncated it, because we've cut it, I have to just say approximately equals to 0.43. And that concludes this set of examples. So remember, these examples are just taken straight from the textbook, so you can have a look to see how the textbook questions work. Effectively the same thing. What you'll need to do is you're going to head to the page 145, which is exercise 3F, and the questions that you will be attempting from 3F is question 1. Let's zoom that back up. Yep, here we go. Is question 1, question 2, just the 2 left-hand columns. Question 3, the 2 left-hand columns. 4, 5, 6, and 7, the 2 left-hand columns. Okay, that's all you'll need to do with the questions. And if you want to enhance your learning, you are more than welcome to try to do any other questions afterwards. But for now, let's just keep it from 1 to 7, all left-hand or 2 left-hand columns, excluding question 1. If you have any questions regarding the set work, you can always send a chat to me, and I'll see you guys. I'm pretty sure I'll see you guys in the next video as far as I'm aware. Till then, stay safe, wash your hands, and I'll see you soon.